Therefore, if some people arrive late, it will not be a problem. Also, I don't expect you to remember what we were exactly doing, but this is what we want to prove. Theorem. This is going to suppose that it's a solution that take values in L2, strong solution of this linear problem. In Rn, where the potential is in L infinity in both variables. Moreover, the limit when R goes to infinity of the L1 node in the interval 0, 1 of the L infinity node of Rn minus the volt is 0. That means that you need some decay of the potential. Constant will not do it. If exponential, then you're going to beta square u of 0 and exponential of alpha square u of 1 are in L2 with alpha multiplied by beta less than 2, then you are 0. Let's try to place this into the framework that we were using, because we were writing this A in the top with a pi and all these things, right? Okay, this is what we will prove today. Okay? Why this makes sense. And how far are we for being sharp? Okay, let's recall L2 Hardy, uncertainty principle. Is say that if you have a function and his Fourier transform also decay like this, if A multiplied by B is more than 1, you have F is 0. In fact, equal to 1. Okay? And we saw that to prove this, you need some kind of analytic function techniques. Right? Then we saw that if we you can write the solution of the linear free Schrodinger equation in this form. I don't remember, maybe the signs are wrong but in the exponent, but that's not so important. All these Fourier transform evaluated in x4 pi t. Therefore, if you translate Hardy principle to this function, you call this f. This is not going to change the L2 nor. This is a constant for you. And take t equal to 1 to simplify your life. Then you will finish with this. You call this f. Then you say if f exponential of a pi x squared and the solution, okay, this is, and the solution at the time 1 exponential of b pi x squared belongs to L2 with a multiplied by b larger or equal to 1 over 4 pi squared and a be positive, then you are 0. How you translate this into this? You think that this is your function, f. You plug it here. It doesn't make any difference in the L2 sense. And then you take the Fourier transform, and the Fourier transform of f is going to be basically u. If you put equal to 1, you have this. Since you evaluate it in x over 4 pi, this factor appears, and you have this 0. Okay? Now, since we have this pain now that we don't have the a and we don't have the pi and all these things, let's see what are we heading to. Then let's translate into this. You have that u0 still, this is for the free Schrodinger equation. There is no potential. Then you have this x squared over beta squared u1 exponential of x squared over alpha squared. That means that you are writing that for you a pi is 1 over beta squared pi is equal to 1 alpha squared. Then what is the condition? That AB larger than this reduced to a times b is equal to 1 over pi squared alpha squared beta squared. Then your condition is that this number, okay, then this is going to be larger than 1 over 4 pi. Then the square die, and you have, let's see if you agree with me. Then this is this number larger than this, the square die, you have 1/4. Is that okay? This is the condition. Okay. Or if you wish, that means that we are a little bit off, right? We don't accept to be that the coefficients, we have to go a little bit, this has to be smaller for us to kill this. In the moment that alpha multiplied by beta is smaller, you are asking for this to be larger. We are off. The question is, can you get to the chart 1? Yes, there is another paper that we get to the chart 1 with the same kind of potential, except that we lose equality, and we prove that the equality doesn't hold with potential. Okay? Okay. Then we are off. Remember, this is the result should be alpha, beta less than 4. Okay? This is the chart 1. In the free case. Okay. Also, let's recall something that by using the conformal transformation of, there is a transformation, you can reduce everything to work with alpha equal to beta. Remark, by the transformation that we discussed that time, by the Apple or conformal transformation, we can reduce to work with gamma equal to 1 over alpha times beta. That means that we are going to work with gamma. Okay, this is alpha. More than 1/4, right? Is that correct? Okay. then the theorem is going to be stated, it should be stated with the same. Then you have that. Is the solution at the time 1 and at the time 0 is finite with gamma larger than 1/4, then u is 0. And this is what we are going to prove. And then we are close to prove the chart result. We are not losing generality by assuming the same decay at 2 times because we have the conformal transformation. Is this clear before we start? Then we can erase all this because this is just to remind you where. And of course, if we prove that, we have a uniqueness for the nonlinear problem that I will not state. But we stated that last time. You will see that the proof follows the idea that we did for the constant coefficient without using analyticity. But we will not require that you remember anything. Okay, we are going to assume 2 things that we will prove later. By the time being, to be proved, okay. Let's call this lemma 4 or lemma 3. Lemma 3 says the following, that for every epsilon, for every mu, for every r, for every function that have compact support in Rn plus 1, you have the following estimate. Okay, this is a typical Klainerman estimate. This exponential function up to here is what we used the last time. We are adding the part that will help us to be positive defined. You don't have to remember this is exactly what we used last time. This is a remainder that we need to add to make it positive defined. This is saying that this is the inhomogeneous part of. This will give you the inhomogeneous part that will be b multiplied by g if you apply there, and this will be the original function, of course, but you have to have compact support to apply this. And then there is nothing to justify here because you have compact support. Then all the integration by part, all the decay, everything is perfect. Right? Of course, your function doesn't have compact support. You will have to truncate the original one. We will prove this, and we can prove this in 2 ways. One will be to follow what we did last time and prove logarithmic convexity, but we will not do that. We will do something simple that is a straightforward Klainerman estimate. Okay. We need one more thing. Remember that we are here. U is C2, C of 0, 1, L2 art n, and we know that this is true. By the way, this condition is 1/2 here because this is not, we are not proving the chart one, we are proving this one. We are proving, this is what we are proving, this is the chart one that we are not proving. Okay? Then, this, if you have this then, this is lemma 4. Then you have this estimate. Okay. Then there exists n positive, a constant, such that this quantity is less than n exponential of n L infinity nor of the potential in 0, 1 multiplied by the supremum in T of the L2 nor with the weight. Assuming that this constant is bigger than 1. What is important, the only thing that is important of all this is the following. We have this nice estimate that requires this one to have compact support. We have this estimate that tells you when you control the L2 nor at the time 0 and at the time 1, if we can apply the estimate of the last time that the potential is small, right? You will have control over this. But moreover, you have control of a little bit better. You have control not about u, x multiplied by u, and the derivatives of u in which nor? Not in the supremum in time in L2 in space. It's in the L2 in space and time, with something that die at time equal to 0, at time equal to 1. Okay? We will prove that too. It's a little bit tricky, but that's it. Okay, now that we have everything, let's go to the proof. And let's write what we are proving in the way that we are proving. Gamma more than 1/2. Let's put here gamma. Okay, let's go to the proof. Assuming these two lemmas, we go to the proof. Okay. Proof. Given this gamma, choose mu and epsilon such that you have the following inequality. It's going to look extremely technical, but let's try to put the ideas. The only thing important are the ideas. I mean, all this is going to be quite technical. This is Okay, what happened? You have a number larger than 1/2. If this number is larger than 1/2, you can choose epsilon sufficiently small that still this number is larger than 1/2 and you are above here and this is above this one. Why the 3/2 and all this? Well, you will see why. Okay, look, this number is a little bit more than 1/2. This is strictly more than 1/2. Then you can still put mu there and epsilon. This is okay. Okay. Let define this function to be equal to 1 when you are less than m, to be equal to 0 when you are larger than 2m. And m is going to be a big number. M is going to be larger than r. Right? This function is infinity compact support in Rn. How big is the derivatives? Well, this function goes from 1 to 0 in an interval of length m, right? Then the derivative is like 1 over m. Is this clear? This function is of this source. Then the derivative is very small. Okay? Okay, let me write the function here. This is going to be the truncation in the x variable, because we need to have compact support and we don't have it. Okay, what is the truncation in the t variable? Phi r will be the following function. It's a function that goes from 0, 1 into r, that is have compact support in that interval and have this property. Phi r of t will be 1 when you are far away 1 over r, 1 minus 1 over r, and you are 0 if t is between 0 and 1 over 2r union 1 minus 1 over 2r, 1. Okay, how is this function? This function is like this. It's symmetric. Okay, then let's do it like this. It's 0, 1, you have here 1 over 2r, 1 over r, and it's symmetric here, 1 minus 2r, 1 minus 1 over r, you are 1 here, and then you are 0 here. Okay. Now this function has the opposite. It moves in this interval of length 1 over 2r decrease 1. Then the derivative is like r. You want like r. Okay, whenever the derivatives exist. I mean, this function will be 0 here and 0 here, right? Okay. Is this okay? Okay, who is going to be our function? Please, if you have any question, we are not really in a hurry by any means. Okay? Then, of course, everything depends on r, and then g, that really is I'm not going to write it like g of t is a function of n and r because it's going to be truncated is the original u that you have multiplied by the truncation in x multiplied by the truncation in t. Now, this function has compact support. But, of course, doesn't solve what you want. You have some error now. Then notice the support of G is compactly contained in Rn by 0, 1. Also, what is the equation that you satisfy with G? Well, when you take derivatives in T of G, then you have a problem when you hit here. Then it's going to be minus u of minus u theta p prime. When you take the Laplacian, then you have a problem when the Laplacian hit, the gradient hit here and hit here, then this will be 2I gradient of um gradient of u, and then you have the problem when the Laplacian hit here plus I plus I theta m u Laplacian theta m 0. Is this correct? Okay, let's call this one the term E1, and this is the term E2. And let's see where are they supported. Okay. See, E1, the support of E1, what happened with E1? Well, this one killed the part at infinity in the x variable, but this one tells you that you are really located here. Then the support of this is contained in the xt such that x is less than m or 2m, because more than 2m you are 0, and t has to be here or here. Then t is between 2 over r, 1 over 2 over r, and 1 over r, or 1 minus t is between, and t, or t, is between 1 minus 1 over 2r, 1 minus 1 over r. Is this correct? You have the only way that the derivative is not 0 is that you are here or you are here. This, you can write it in a different way. You're going to put that this is 1 minus t between 1 over r and 1 over 2r. It's the same business. Then that means that t is between this and 1 minus t is this. This is the support of that. Okay, let's see how big is that function in this part of, how big is this function in that domain. On this set, you have mu by x plus rt1 minus t e1 is equal, okay, let me write this in the top, then I don't lose this line. Okay, this is a square, then this is mu, then this is x squared plus twice this multiplied by the first component plus the square of the second component, that is r squared t squared 1 minus t squared, right? Okay. I want to know how big can be this number. And this is mu, this is x squared plus, this is less than 2, the absolute value of x. You have r here, but now you have here t, and t is smaller than 1 over r, and 1 minus t is also smaller than 1 over r. Therefore, this is less than 1 over r squared. This quantity is less than 1 over r. This quantity is less than 1 over r. Then you have 1 over r squared. And here you have a square, and this one is less than 1 over r, but you have a square here, you have this. Right? And using that t is less than 1 over r, and 1 minus t is also less than 1 over r. Then you have, this is equal to mu x squared plus mu 1 over r squared. And for this term that you have here, I will use this estimate 2x, this term that you have here. You write it in this way. This is 2x 1 over r. That is equal to 2x square root of epsilon 1 over square root of epsilon over r, and then you use the trick that a multiplied by b, 2 times a, b is less than a squared plus b squared, you have this. There is a mu here. Therefore, you have bound this 1 plus epsilon x squared plus mu 1 plus 1 epsilon. Okay, this is not. One over r squared. It is okay. I mean, I use the trick that a multiplied by 2 times a multiplied by b is less than a squared plus b squared. I use that here, and then I plug it here. This with this gives you this. This with this gives you this. And now you have the property that 1 plus epsilon multiplied by mu is less than gamma, plus gamma over epsilon r squared. 1 over r squared. Okay.
Support of E1 is in that set, but there is something strong missing there, because 1 minus 1 over 2r.
Where are you?
Greater than.
Where are you here?
No. Yes, the other one.
This one?
Yes.
Uh-huh.
I think there is the other sign important.
This one you don't like?
Yes, but also the other one. Because you have that 1 over 2r is smaller than 1 over r, right?
Okay, then it should be the other way around?
Yes.
Okay. Is this like this?
Yes.
Huh? The other one was okay?
Yeah, the other one.
This is okay?
But is it possible for number t to be smaller than 1 over r?
Let's see. Give me 1 second now. We're saying that t has to be here. This is okay now? And when I take this was here. And now this is okay? When you take derivatives, you have to leave here. But, okay, the problem is that this is wrong. Okay, now, okay. Okay, then this is 2, this is r, and now we have this. Okay, thank you. Okay, now what is this other, the other?
Yes, because is it possible for a number t to be smaller than 1 over r, and also 1 minus t to be smaller than 1 over r?
Yeah. No, you're here or here. Okay, your support is here. I mean, I'm not saying that you have both. It's or. Or. Because your support, when you take derivatives, you are here or here. That means that you are very close to 0 or very close to 1.
But when you put this relation
Here.
yes, in the other one, what will you use?
Unbound this from above. Okay, if I am the support, okay, let's go here. If I am in the support, okay, you are, okay, let's see. Okay, I'm taking that I am here and here. That's your complaint. Okay, I understand that complaint. Let's see, how can we get rid of that? Okay, you understand he is completely right, and you are here or here. We have this estimate. We cannot, one of the two of these is going to give you that you are less than 1 over r, but I cannot put the two of them. Okay? Then I have, the only thing I have will be this one. Let's see, this is less, one of the two is less than 1. And in the support of this is the only thing I have. Okay? Okay, let's go back to see then if we still have a proof. Thank you. Thank you. Okay, let's go back here and say we have, this is like this, then this is less or equal to, wow. Okay, now we have to be a little bit careful because we don't want to. Okay, what we have here is, this is like this, plus 1. Okay, this is r, 1 over r, plus r squared, 1 over r squared. Then what we have is mu x squared plus 2x plus 1. Okay. Now, and I don't care to pay. Okay. Then I have to be a little bit more careful here. I have this. I can put epsilon square. Okay, that will not be a problem. Okay, this is, then I have 2 over x is less or equal to square root of epsilon over x, 1 square root of epsilon, 2, this is less than epsilon x squared plus 1 over epsilon. Then this is less than mu x squared plus epsilon x squared plus mu that coming from here plus 1 over mu 1 over epsilon. Is this okay? Now, I have this term here. This one is here. This is coming from there. Then this is less than mu plus epsilon x squared plus mu that get 1 plus 1 over epsilon. And this is less x squared. And what do I have here? I have that number. Okay, this is going to be epsilon 1 plus, this is mu over epsilon. Is this okay? Okay, thank you, Luis. Please, don't believe what I say, okay? You have to be critical. Okay, we have this. On the support of the first inhomogeneous term, you have that. Okay. What is the support of the second term? The support of the second term, you still have that this guy doesn't, the derivative hit this one. Then you are here. You are in the x t that belongs to Rn 0, 1, such that x is between m and 2m. T is 1 over 2r, 1 minus 1 over. Therefore, on this support, how big is this function? Mu by x plus r t 1 minus t e1 squared will be equal mu, you have x squared. This is going to be bounded by 1. Then this is 2r by x. Then let's put less or equal. Plus r squared. And you do that r multiplied by x is the same business. You have that 2r multiplied by x is equal to 2x square root of epsilon r square root of epsilon. Then this is less than epsilon x squared plus r squared over epsilon. Therefore, this is less than mu x squared. This one is bound by epsilon squared r squared over epsilon plus epsilon squared. That is going to give you mu plus epsilon x squared plus r squared multiplied by 1 plus 1 over epsilon. And that gives you less than gamma x squared gamma r squared over epsilon. Because you have this, okay, this is gamma. Is this okay? Okay. Seeing that we are okay, still okay. Now, let's apply this lemma to our function g. Can we do that? Well, yes. The only requirement is that g to be compact support, and our g have compact support. Then what are we going to write? Well, we are going to write that this part is going to be whatever you got in the homogeneous term. You're going to get this is bounded by this. And who is this? All this is the homogeneous term. This is what you're going to have now in the right-hand side. Therefore, what you have is this. By lemma 3, you have this estimate. I don't see. We have R square root of epsilon 8 mu. Okay, I'm not going to write. Let's put the whole function here. G in L2, everything is in a space and time 0, 1 is less or equal to what? The same function that you're going to write. Okay, let's be careful. We are missing one term. What is the term that we are missing? Who is our u? Who u satisfy this equation? Then we're missing what? The v. Okay, then this is equal to this plus this. Plus, minus, you pass to the other side, is I, B, since you multiply by this, is going to be U, TM. Is this clear? When you apply the derivatives in T minus I, the Laplacian to here, when that hit here, you have to substitute that by BU. And this is what you have here. This is okay. I was missing this term. And in fact, this is equal to this plus this plus this. Are you with me? Okay. And who is this? This is G. Okay. Then this is less or equal to the same business, B multiplied by G, and now using the triangular inequality, L2, plus the first, this term, plus this term. These are the homogeneous part. Are you with me? Okay, we have three terms now in the homogeneous term. The first, we used to have 1, but the truncation in T and the truncation in X give you 3 ones, but this is the same kind of term. And this is another kind because the derivative hit in mu, in rho. Here the derivative hit in theta, and this is what we have before. Okay. Okay. This is the key of the matter. Are you with me up to here? Okay, how big is B? B is in L infinity, right? Therefore, the first term here, notice that this quantity, e to the, all this is bar phi, B multiplied by G in L2 is less than B in L infinity in space and time multiplied by, is this okay? Then this quantity that you have here is bounded by this quantity. If you can take, you're going to take R very large. In particular, if R is twice, if epsilon is fixed, mu is fixed, suppose that this number is twice this one, then you can pass this to the other side and pay by 2. This side is already bigger than this one if R is sufficiently large. Then by paying with 2 here, with 1/2, I can erase this one. Is that clear? This is always a trick in this. Therefore, we have this term. So we only have this. For R, if R large enough such that R multiplied by epsilon A mu is larger than twice the B L infinity, then we have that this is bounded by this and this, maybe with a 2. Then we have this, R it's clear that this is L2 in space and time, less or equal than twice this one, E1 plus this one, E2. Okay, then from the 3 term, by hypothesis, you get rid of this one. Now we want to get rid of this, the one that has the derivatives in of this one. Okay. Now we are here. Then okay, let's go to this term. Where is this guy supported? E2. Well, E2 is supported. Okay. What is a good bound for this? Okay, let's go here. E2 is supported. Where do we have E2? Here. Then this is let's see if you agree. This constant will go out. This will go out here. Then you have the rest of all this here. And here you have this term that is E2. Okay. In L2. Okay. Okay. Remember, what is the characterization of E2? The characterization of E2 is that you have the derivatives in x. When you take derivatives in x, in theta, what is the bound that you have? What is this? When you take derivatives in, what is it? What do you know about the derivatives in theta? Here you have derivatives in theta. Here you have derivatives in theta. When you get derivatives in theta here, how big is this function? 1 over m. Then there is a 1 over n here. Then you have, this is less. Okay, and now let's copy what you have. This function is bounded by 1 over m. This is the gradient. You can't fill all this. This is going to be u, gradient of u. Then you're going to have this is u, this function is bounded, this function is bounded, this is bounded by 1 over n, this is bounded by 1 over n. At the end, you have this. Is this okay? You have here the gradient because you share the derivatives. Here you don't have anything. This is bounded by m squared if you want, but you don't care. M is going to be huge, and it's in the denominator. This is bounded by 1. This is I. This, forget the 2, and so forth. You have this bound. Do we agree? Okay. Now, look what happened. This is something that depends on t. Right? You can put it inside here. This is L2. You can put this part in the L2 node in the time. This part is bounded. This with this in L2 is bounded. This with this weight is bounded. Why? Because you have this estimate. Can I use this estimate? I mean, I have the estimate in L infinity of this, of the U by itself. My problem is to bound this one. Remember that. Okay? Let's go here. Okay. Let's go here. This is bounded. This is bounded. Okay, you're going to say, but you don't have a good bound when t is close to 1 or t is close to 0. Look this term. Are you really close to 1 and 0 here? No, because this function gives you that you have a distant r. Paying with an r, or r squared, some denominator, I can bound this one, I can bound this one. But you say, well, but you have the x here. That's okay. The x is huge because you have, I mean, this is what is important for you is what, at infinity. Then, since you have the derivatives, this is going to be for x between m and 2m. And for t, between 1 over 2r, 1 minus 1 over 2r. Then, on this domain, this estimate gives me control of this one, because this is the support of this. Are you with me? But now I can take m to go to infinity. Then what do I get? I have something bound here, and I have n in the denominator. When n goes to infinity, this disappears. But I have the control of this because I am far away from the boundary. And these estimates are quite good when you are not far from the boundary. Then this term is really not there either. Is this okay? Okay. See, really, you are using this part. You are using that when x is here, this is better. If you bound this, you bound this. Okay? This is a better estimate than what you need. Okay, therefore, we don't have that either. You take n goes to infinity. this part disappears. Therefore, the only thing that we have is this one. Of course, and now we have maybe 20 here. Okay, and M is infinity. Now you cannot use that you have compact support in the M direction and so forth, because you already have that. Okay, now let's go. This is what we have. Okay, now if G is equal to U on this domain, on the ball of center 0 and radius epsilon 1 minus epsilon squared multiplied by R over 4 multiplied by 1 minus epsilon over 2, 1 plus epsilon over 2. Is this correct? You have from the beginning this, you take M to infinity, then it's not, this is much less than M. This is true all the time in the X variable. In the T variable, you're always 1 if you're here. I mean, you're going to, if R is sufficiently large, this is true. You are 1 there. Is that correct? G is equal to U when you are in this domain. If R, okay, R large enough. What happened in this domain? Okay. What happened in this domain? How is your function? How is this function bar phi? Bar phi on this domain we have that this quantity is more than this one. This is going to be the largest part. This is going to be the smallest part. Then T is here. Then 1 minus T is also there. Therefore, I'm trying to bound this from below. I have to take the smallest value of this, and I have to subtract this one. Then this is more than this. This one is R. This is 1 minus epsilon, 1 minus epsilon squared, minus how big is, and now I subtract the largest possible value of x, is epsilon 1 minus epsilon squared R over 4. Minus let me write all this. This is 1. And I need to subtract I want this to be bound from below. I put this term as the largest one. I use that t is at most 1 minus epsilon, that 1 minus t is at most 1 minus epsilon. I have a square here. Okay? This one is bounded by this. I subtract the largest possible value. I have this. Now I'm going to subtract the largest possible value that I have here. This is 1 minus epsilon r. How big is t? Well, t is bounded by 1 plus epsilon. Then you have 1 plus epsilon squared, right? But you have a 2 here, then you have 16 mu multiplied by 4. Let's see if you believe that. I use triangular inequality here. The only thing that I'm using, plus r, t, 1 minus t, e1 is larger than this one minus this one. Then this is t is at least 1 minus epsilon, 1 minus t is at least 1 minus epsilon. Then this is r, 1 minus epsilon squared over 4. Then I have a 4 here. Okay? X is bounded by this one. This is okay. This is the only thing I did in the first part. In the second part, I have to do the opposite because I want a bound from below, but I have a minus. Then I have to put the largest one. Okay, who is this? This is mu multiplied by r multiplied by 4. Then this is what? 1 minus epsilon squared, common factor of what? Of 1 minus epsilon. And all this, okay, I have the square. I have to be more careful. Okay, this is equal to mu r 1 minus epsilon squared 4 that multiply common factor 1 minus epsilon. All this is square minus 1 plus epsilon cube r 64 4 mu 16 or something like that. Okay. Then this is equal to mu r square 1 minus epsilon to the power 6 minus, and I have 16 here, 1 plus epsilon cube r, all this, 4 mu 16, that you can write it in this way. R squared 16 mu common factor of 4 16. Where do they have the 4? Okay. And you with me up to here? Okay, we have 2 more computation and we finish. Okay, you have to help me with this one. Okay, this is, maybe this is 64. Because there is 4 here, this is 60. 4 times this is 6. 4 times 16. 4, 1 minus epsilon to the power 6. 1 plus epsilon to the power 3. And mu squared here. And I have, okay, I have this square. Where did I get this square? By the way, this is a square here. This is r squared. This is r squared. I copied that wrong. This is r squared. This is r squared. This is r squared. Then I have 4 mu. Mu squared. Thank you. See, the r squared was there from the beginning. I forgot to write it. Then if you put all this, you have this. Okay, what do we know? That this quantity is strictly positive. That's this horrible computation here. This is strictly positive. Okay, we are very close to finish. Don't give up. If you haven't given up yet. Okay, we have this. Then we have that this part, we are trying to analyze this guy, and this guy happen to be G happen to be equal to U in this domain. And in this domain, you have exactly that this is bigger. What happened in E1? Oh, don't tell me that I erased that. Okay. We copy that for E1. In E1, we have this. Okay, let's copy that. And that was the correction. We have to be careful. On E1, we have that T go 1 over 2R, 1 over R, union 1 minus 1 over 2R, 1 minus 1 over R, and X, okay? It was less than M, but we took M goes to infinite, X in R. Then we go, what was the bound that we go for here? What's the bound that we go when X T belongs to the support of E1? What was the bound that we go for phi? We get mu of X plus R T 1 minus T E1 is less or equal to mu 1 plus epsilon X squared plus it is equal to X squared. That was the bound that we got, right? Yes, but okay. But we took n to go to infinity, okay? Okay, x goes less. Okay. We need to put order in the way that we're going to take things to infinity. Okay. Then let's see. What do we have here? We have R, all this, maybe with a 4 here. Then if we put things together, what do we get? That this one is U on this domain. And on this domain, this quantity is larger than this. Then we have this. You have R, something that depends on. This is not going to be important anymore, but let's write it. You have this. You have exponential of R squared 64 mu multiplied by this crazy number that is positive 4 squared 1 minus epsilon 6 minus 1 plus epsilon cube. This is a positive number multiplied by U, the L2 in which domain? In this domain. In the ball of center 0 and radius R, epsilon 1 minus epsilon squared R over 4. multiply in the time variable in 1 minus epsilon 2, 1 plus epsilon 2. And this is bounded by what? Okay. By this one. Okay, and now what is that one that we have here? This bound, how big is this bound? Let's write this here. This quantity is bound by this one that we have here, and this one is bound by this. Let's write this one. This is less or equal E1L2. Then let's see. Okay. Then when we are here, this is less. How big is the exponent when you are there? When you are in this domain, how big is this quantity? Forget this part that is negative. You can forget that. You are bound this from above. Then this is less than this. Okay, and let's write who is E1. E1 was exactly equal to another one. What is E1? E1 is theta m of x, the cut in the t variable multiplied by u. Okay? When you take derivatives, this is bounded by 1. Remember, this is bounded by 1. This is bounded. This may grow with r, because you are taking derivatives of something that will have this. Then the bound of this is r. This is 1. The bound of this is r. This is mu. Then you have r, u, L2. Okay. Okay. Are you with me up to there? Okay. See, if you forget the r for the moment, if you don't have the x, if x is less than 1, you can use that you are in L2. If x is more than 1, you use this estimate. And can you use this estimate? Yes, because you don't have a problem to be close to 1, because t here and 1 minus t is a bound that gives you r's there. You have this. Then this one will be bound by this. Maybe you have to pay with another power of r. Then this maybe is, in the worst case, is r cubed and the estimate that you have there. Rho epsilon e rho x squared of x u L2 1 minus 1 over r plus the part, if you are very close to L2 to 0, you can bound this by this. Do you believe that? Okay, let's do it carefully. This part, this one goes out. This has nothing to do with the x. Why do you put r cubed here? Well, because I need to use this estimate. And you're going to say, well, what happened if I want to use this estimate and then I have this support here. Right? This tells you that you are living only in this area. And in the other one, symmetric here. Then you're going to say, well, do you really need this? Yeah, well, suppose that, when r goes to 0, this part, to use that, you have to divide it by r and do that. Then you pay a price with this r. Okay? Then you use this estimate. You have this is bounded. Okay, I have to put this. Okay, this is what I mean. I want to put this estimate there. Is this okay? Please, we have to discuss whenever you want here because we finish. I will not write any other quality, we finish. Okay, if you put this, you have to multiply by r. Is that what bothers you? Okay. Okay. I have this estimate. Okay. Suppose that I put t. I want to put this estimate here. Then how small can be t? Then I want to take this one out, right? Then t is larger than 1 over r. Then 1 over t is less than r. Then I pay with an r there. If you want, I pay with the square root of r because it's a square root of r. Then this is less than 1 over r t, because I'm living in this domain. T more than r. Or more than 1 over 2r. Then I multiply by this, then I have this 2r. Then I have 2r. Okay. Then I have to pay with an r by having this truncation here. Okay, but I pay with this r, if you want, with 2 here, and I have a square root. Really, it should be this one only. Okay? It doesn't matter. Okay, this is bound. This is bound. Depend only of the data. Okay, then how fast this guy grows in R? Like R squared. How fast this guy grows? This is positive. Then when r goes to infinity, what do you get? You get that a polynomial bounds on exponential. And this quantity is increasing. Then what is the only possibility? You have that now epsilon is fixed, mu is fixed, everything is fixed, take r goes to infinity. You have a polynomial bound of some exponential. This is strictly positive. Then this quantity is growing exponentially squared, if you wish. This is increasing in R. This is polynomial in R. When you can have something like this? When R goes to infinity. This has to be 0. But if this is 0, you finish. Then this function is 0. For some interval of time in the whole space in the limit. Then you have finished. Okay? Okay, then okay. Any question? Please ask question because this is a very long computation and You have a lot of parameters. You have the m that you took to infinity before you move and then you take the r to go to infinity afterward. Okay, the m was larger than r. It was not a problem. Okay, and the trick was to use this Klainerman estimate and see that you have 3 terms, and the 3 terms, one is inhomogeneous that you absorb there, the other one you have a good location, and the third one is the one that you are doing there. This is the one that gives you the group. And if you go to the proof that we did for the L2 Hardy uncertainty principle without analyticity, it's the same idea. This is the same domain. This is the same function. Of course, we put this one to have everything from the beginning okay. It was exactly the same thing.
So when you put the x in the less than quantity,
Yeah.
you need to pay a price. The x, the last one.
This one?
Yes, the x inside. Models of x by u.
Mm-hmm.
So don't you need to pay a price to put this?
No, because this is bounded with the x here.
But the previous model don't have the models of x.
Okay, I see. I put put your domain in 2 pieces. If you are less than 1, right, you use this. If x is less than 1. If x is more than 1, you use this. Is that okay? Then you have 2 pieces. If x is more than 1, you use this one. That gives you something bigger. If x is less than 1, you put that. Then the exponential, everything will be bounded. Okay? Let's make a small review of a point. We have that we define G to be the cot in the x, the cox in the t of u. And we have that u satisfy this business. B of xt, tm of x, phi r of t, u, plus, maybe minus, 2 gradient of m, gradient of u, phi r, plus, maybe there is an I here, minus I twice. Then second derivative here, u phi r plus, when the derivative hit, this is G. Okay. And you can write here a function. If you multiply, remember that phi m was something like this. You can multiply here phi 2m and do nothing because this is already 0. Okay? Now look, can you apply the estimate that we have before? Your initial data is, you have, this is like G here, right? Then this is the inhomogeneous part. This is an external force. And this is the your G, and this is your potential for the G. Your potential for the G is something that is dying at infinity. This hypothesis, this is supported, right? Okay, what I'm trying to say is, I don't want to say anything. I forget that. Okay? This is what we did. Okay, what should be our next step? Let's see how you prove this. Okay, we have two goals. One is to prove this, and one to prove this. If we prove these two, we are completely self-contained proof. Okay? Okay, let's try to prove this. Okay, let's prove lemma 3. In abstract. And this is the idea of Klainerman estimate. Suppose that you have an equation that you can write in this form. A is symmetric, A is skew-symmetric, operator, S is symmetric. Then you say, okay, I'm going to compute the L2 north square of this. I'm not assuming that this is 0. I'm going to have inhomogeneous terms and so forth, right? Okay, this is equal to this part that is going to be the derivatives in T. Okay, I'm going to do this in L2, in Rn plus 1. Okay, X is in Rn, T is in R, and this is skew-symmetric. Derivatives in T is skew-symmetric, okay? This is equal to this. Minus 2 times the real part of SF multiplied by dt of f minus a of f dx dt. Is this okay? You have this one. You're computing the L2 of, the north square of a vector. This is of the difference of two, the north of the first, the north of the second, and this is minus the inner product of the first with the second. Okay. Then what do? You throw away this and this. This is less or equal to this. Then twice the real part of this is this one This is okay. Okay, let's leave. This one is symmetric. You can pass to the other side. This one is skew symmetric. You can pass to the other side, and you have this. Then you have, let's see what you have here. I don't want to mix up everything here. Then this one, when I pass this to the other side, I have this. And this one is, I pass this to the other side, symmetric is st of f minus a of f conjugate. And of course, I mean, everything is a double integral. Okay, what do you have first? This derivative in t is going to hit this operator and is going to hit this one. When it hits this one, it's something that you already have here. Then this is equal to st of f. This is when these derivatives hit here, because when this derivative hit here is something that you already have with a minus sign. Plus, what do you have here? You have minus as of f, and here you have plus sa of f. Then what you have here is exactly something that we haven't done several times. This is the commutator. This is okay. And this is what we are going to prove this. We are going to use that here straightforward. And this is the idea of, this is the idea of Klainerman. You want to prove that this is bounded below, you throw away this, and you want this part to be positive defined. This is what we did for the. Okay, in our case. Call this f to be all these functions. Therefore, you have that you call all these functions this is what you have here, right? Is equal okay, I wrote that this is f, the f that I want. Therefore, what I'm saying is that f is exponential of bar phi g. Therefore, what you have here is exponential of bar phi, the operator applied to g. But who is g? G is exponential of minus bar phi f. And when you apply this, these are going to cancel at the end, but you have something like this. This is dt of f minus a of f minus f of f. When a is symmetric, A is q-symmetric and S symmetric, and they are equal to this. A is the q-symmetric I Laplacian plus 4 mu square I multiplication by this. And S is equal to this more. Okay, so for in computation, you have when the derivatives of t hit here, you collect it. When the derivatives of t hit here, you have a multiplication by the derivatives of t of that. Then you have a long term. Then the gradient, the Laplacian hit here is part of your business, is here. Then when you split the operation and so forth. Yeah. Okay. Then we will finish in 5 minutes. Then if you do the computation, the derivatives of the operator t, the operator s with respect to t, plus the commutator of these two is a long computation, but it's equal to this. It's a long computation, but it's what it is. I mean, it's therefore, you have that ST as an operator, the commutator between S and A applied to F, inner product by F, an integral in space and time, is going to be equal to this one that is going to give you positive defined because it's negative, but it's Laplacian, you integrate by part. This is positive defined. Okay, this is not positive, this is positive. You don't know if this is positive, and this is positive. I mean, you have almost everything is positive except maybe this one that you don't have it, and this one that you don't have it. But you can write this in this way. This is equal to 32 times mu cubed x plus r t 1 minus t e1 minus r 16t mu square e1 square f square dx dt plus epsilon r square 8 mu integral of f square dx dt plus 8 mu derivatives of x1 of f square dx dt plus 8 mu I dx1 minus r1 minus 2t 2f square, I have to put f here, dx dt. And if you do all this, you will see that this term survives because this is positive, this is positive, this is positive. Then all this is larger than this. And this is exactly what you are trying to prove. Let's put together everything and we finish. Then this one is this quantity. This one that you have here is this quantity. And this quantity is what you want to start here. Okay? Therefore, this one is equal to this. Then you did all this, and you finish with this quantity. And after you do the commutator and all these things, you see that this is positive defined. But this is equal to what? Then you have started with that, and you have finished that this quantity is larger than 8 epsilon r squared a mu dl2 north of f. But who is f? F is this. And this is what you wanted to prove. And of course, you are missing a square here. You are missing a square here. And that's the reason why you have this factor there. Then you can see that this is very similar to the proof that we did that something was logarithmically convex. But it's much simpler. You're not trying to prove something so sophisticated. You want to prove that the inhomogeneous term controls this one. Okay. Next time we have to prove what we erase here. And we will start a different business. We haven't been working within the interval 0, 1 in time. Let's see what we can say when you want to work in the whole line in time. It will be completely different. Any questions?